The next topic we're going to discuss are colligative properties. Now, colligative properties refer to any physical property that can be affected by a solute, and the big distinction is that colligative properties are properties that depend on the amount of solute, not specifically on what type of solute. So you can put in, say, sodium chloride or potassium chloride, and they will have the same nominal effects on the four colligative properties that we'll look at today. Vapor pressure, freezing point, depression, boiling point, elevation, and then osmotic pressure. Colligative properties depend on the amount of solute that you put in. So we also have to be aware that when we put in, say, 4 formula units of sodium chloride, we are actually putting in 8 ions. Again, when we're talking about ionic compounds, we have to be aware that dissociation occurs and that the number of ions will change depending on the stoichiometry of the dissociation. Okay, so one of the first colligative property we'll discuss is vapor pressure lowering. So we talked about vapor pressure. It's when the rate of evaporation and condensation form or rates equal, and the pressure of the gas in that closed container. Okay, it turns out that if you add a solute to your solution, the rate of vaporization is reduced, therefore lowering your vapor pressure. Part of the reasons why that is that solute particles start to take up surface area, so not the solvent molecules cannot leave as easily. And then the second part of the story is that as the solvent evaporates, it's actually becoming more ordered system, so you're sort of going against entropy. Okay, there's a very simple equation known as Raoult's law that you can utilize to determine the change in vapor pressure. If you know the the vapor pressure of the solvent, which will, and under standard state conditions, and you multiply it by the mole fraction of the solvent, you can get your new vapor pressure of the solution. You can calculate very easily the change in pressure by just subtracting the two. Okay, so let's take a look at the vapor pressure of a solution that contains 99.5 grams of sucrose and 300 milliliters of water. Okay, so we're going to have to use our equation. That it will be the vapor pressure of the solution equals the mole fraction of the solvent multiplied by the vapor pressure of the solvent. Okay. The vapor pressure of pure water is 23.8 torr at 25 degrees Celsius. So really what we just have to calculate now is the mole fraction. Okay, so we have to calculate the number of moles of sucrose, and if we have 99.5 grams of sucrose, we look that up, and it actually has a formula of C12H12 H22O11. And if you calculate the molar mass of that, 1 mole of sucrose, C12H22O11, will have a mass of 342.3 grams. Okay, so you just calculate that, and that is 0.291 moles of sucrose. Calculate the number of moles of water in 300.0 milliliters. We already know that the density of water is 1.00 grams per milliliter. I'll cancel out milliliters. Calculate the molar mass of water, and we find that 1 mole of water is 18.02 grams. And that gives us a value of 16.7 moles of water. Okay? Our mole fraction will be equal to 16.7 moles of water over the total 16.7 moles plus 0.291 moles. That gives us a mole fraction of 0.983. Okay, now that we finally have our mole fraction, we can calculate the the vapor pressure of our solution. So that's going to be 0.983 times our vapor pressure of our pure water, which will be 23.8 torr. And that will give us a vapor pressure for our solution of 23.4 torr. Okay, at the beginning of this section, we talked about how that the colligative properties don't depend on the identity, and of course that there are some exceptions to that. Just like we had ideal gases, we have ideal solutions, and how Raoult's law or any other colligative property can predict those outcomes. Of course, there may be some real world experiences or situations where it deviates from that. Okay, in general, the vapor pressure will always be lowered, but the rate at which it lowers as a function of mole fraction will deviate from ideal solution. If there's a strong solute-solvent interaction, meaning actually causes the interaction between the solute and solvent is favorable, will actually decrease the vapor pressure more rapidly, so it'll take on sort of a concave shape. If it's a very, very weak solute-solvent interaction, that actually increases the vapor pressure rate a little bit faster, and we get this convex shape from it. Okay, we know if we've ever lived up north in the winter, if the roads are icy and snowy, cities throw salt on the roads in an attempt to melt the ice. And that, of course, is because solute lower the freezing point of solvents, and again, a colligative property. The same scenario also increases the boiling point. And here, if we look at the phase diagram of the pure solvent in blue, we can see that the melting point is lowered to lower temperatures, and the red line for the solution increases the boiling point. We've got constants, freezing point depression constants, boiling point elevation constants, that you can use to calculate the change in temperature of these solutions if you multiply it by the molality. And remember, the molality is the moles of solute divided by the kilograms of solvent. Molality, small m. Okay, so let's calculate the freezing point depression of a 1.7 molal aqueous ethylene glycol solution. Okay, so we're going to use the change in temperature, freezing point, molality of this solution, times our freezing point depression constant, which we can look up. If we have a 1.7 molal solution, and we look up the case of F for ethylene glycol, and that is 1.86 degrees Celsius per molal. Molality cancels out, and we're going to get a change in temperature for freezing point of 3.2 degrees Celsius. So what is the freezing point? Well, that's the change in temperature. So if we know that water normally freezes at 0.0 degrees Celsius, and we subtract the change in temperature, 3.2 degrees Celsius, our new freezing point is negative 3.2 degrees Celsius. Okay, our last colligative property that we'll discuss is osmotic pressure. Now, it turns out if you have a semi-permeable membrane, meaning that some membrane where solute particles cannot traverse but the solvent molecules can, such as in this scenario we've got water as our solvent. Okay, what happens is that if you've got a larger concentration at one end, say over here, and a much smaller concentration on the other side of this semi-permeable membrane, water molecules which can traverse this semi-permeable membrane will flow to the higher concentration area in an attempt to alleviate the concentration difference. What that creates in this sort of experiment is a difference in pressure. Okay, so because the water level is higher on the left side than the water level on the right side, there's a different pressure. Now, Osmotic pressure refers to the pressure that would be required to reverse or stop this process. Okay, so if you apply pressure on the left side, you can reverse this process back to the initial state. How much pressure you need to apply is referred to as osmotic pressure. Okay, this has a lot of implications for, of course, biological cells. There's concentrations, intracellular concentrations and extracellular concentrations. Some solutes molecules, most solute molecules cannot traverse the cell membrane freely. There's various processes that transport solute molecules or solute ions, but water can generally traverse the semipermeable membrane known as the cell membrane. Okay, so if the solute levels are similar inside and outside the cell, we have an isosmotic solution, and this would be an example of normal cells. Okay, if the solute levels are greater outside the cell, what's going to happen is water is going to leave the cells to the extracellular solution to try to alleviate the concentration difference. So as water leaves the cell, it shrivels up the cells, and this is known as a hyperosmotic solution. Now the reverse, what if the solute levels are increased inside the cell? Of course, water is going to travel inside the cell to try to alleviate the concentration difference, and that swells the blood cells or any cells, and that's known as a hypoosmotic solution. Okay, additionally, besides just pure solutions where the molecules or ionic compounds are solubilized, we also have scenarios where we can have suspensions or colloids. And we'll discuss colloids in this chapter, or this section. Colloid is a mixture of a large number of aggregate molecules that are suspended in solution. Okay, meaning a large aggregate is a big difference between the solubilized ionic compounds or molecules. And so instead of just one molecule solvated by water or one ion solvated by water, we have a large aggregate of many molecules or ions that are dissolved in the solution. One example is the soap molecules that have a polar head group and a nonpolar tail. They'll orientate themselves so that the nonpolar tails line up together away from the water because, of course, intermolecular forces. Now, these large aggregates of soap molecules, sodium stearate in this example, would be known as a colloid. Many other examples of colloids in various phases, including a very common one, milk, that solubilized fat molecules in liquid. Okay, and that is a colloidal dispersion. One of the outcomes of a colloid solution is that these molecules or ions, or usually molecules or atoms, are large enough that they can scatter light. Light will actually bounce off these large aggregates of molecules. You can see this effect known as the Tyndall Effect. If you see light in a large room, turns out the dust molecules, large aggregates of dust or even water vapor in the air can scatter light. You can see the light beam going through a colloid solution, whereas a normal solution with ions or molecules individually solubilized will not scatter light. The aggregates are not, there are no aggregates that are large enough to scatter the visible